Module 9 is all about fluids at rest. Welcome back to Engineering Physics. What do we mean by fluids? Fluids are substances with indefinite shape as they are able to flow, but they have little ability to resist external pressure. There are two kinds of fluids, liquids, such as water, and gases. Similar with mechanics of solids, fluids also have their own set of study, which we refer as fluid mechanics. This subtopic of engineering mechanics also covers fluid statics or fluid equilibrium and fluid dynamics, which would deal with fluids in motion. Let us introduce the fundamental properties of fluids. First is density, which is defined as the mass per unit volume. In equation form, we can say ρ is equal to the ratio of mass to volume with its SI units as kilogram over cubic meters. As a standard, remember that the density of water is 1,000 kilograms per cubic meter. Read the example. What is the density of a 25-gram substance with a volume of 0.005 cubic meters? Taking the ratio between mass and velocity will give us density, which is taken as 0.025 all over 0.005, and so density is given as 5 kg per cubic meter. The counterpart of density is unit weight, which is defined as weight per unit volume. Unit weight is also called relative weight or specific weight, and in equation we can say gamma is equal to the weight all over volume. Again, as a standard, unit weight for water in SI is taken as 9,810 newtons per cubic meter or 9.81 kilonewtons per cubic meter, and in English we follow 62.4 pounds per cubic foot. Let's have this example. What is the unit weight of a 30-gram substance with a volume of 0.006 cubic meters? Taking our unit weight as weight all over volume, we would have 0.030 for the mass times 9.81 or G all over 0.006, which gives us the answer for gamma as 49.05 Newton per cubic meter. Specific gravity or SG is another important fluid property, and it is defined as the ratio of the density of any substance to that of water. In place of density, you can also use unit weight. And since both substances use the same parameter, specific gravity will be unitless. Take the example. What is the specific gravity of a 30-gram substance with a volume of 0.006 cubic meters? We can solve this equation using density, and specific gravity will be taken as density of the substance with that of water, where density of the substance is its mass all over volume, or that would be 0.030 all over 0.006. And everything is divided by density of water, which will turn out to be 0.005. You can also use the unit weight for solving specific gravity, so unit weight of the substance will be taken as its mass of 0.030 kilograms multiplied by G divided by the given volume of 0.006 cubic meters. And then this unit weight is divided again by unit weight of water, giving the same answer as 0.005. The next concept is fluid pressure, taken as the small letter P. Pressure is defined as force over unit area. And if you recall from the discussion of elasticity, we also define stress as force all over area. Pressure is stress in fluid, thus they have the same definition. In order to appreciate pressure, remember how you felt when you dove into the water at a certain depth, and then compare it at the other time when you dove deeper. You felt more stress or pressure when you were deeper underwater, because there is more volume of water affecting you than when you were in a shallower depth. Since pressure is dependent on surrounding pressure, we can solve total pressure as the atmospheric pressure plus gauge pressure. Atmospheric pressure can be measured using a barometer, and it will yield 101,325 Pascal as the standard. Gauge pressure is the measured pressure, which can be computed as ρ, G, and H when using density, or gamma H if using unit weight. As height is directly proportional to pressure, the bigger the height or the deeper an object gets in the fluid, the pressure is higher. Let's check the example. Two divers have the same mass of 50 kilograms and went to the water as shown. Compute the barometric pressure each of them experiences. Diver A went 10 meters deep and diver B is only 6 meters deep. By using total pressure is the summation of the atmospheric pressure with gauge pressure, that is P atmosphere plus rho GH, the pressure in object A is taken as 101,325 plus 1,000 times 9.81 times 10, which would be equal to 199,425 Pascal. And the pressure in object B is taken as 101,325 plus 1,000 times 9.81 times 6, which would be equal to 160,185 pascals. Another example for pressure is the following. A closed 2-meter width by 3-meter length by 1.5-meter high rectangular container is filled with water. What is the pressure exerted by the water at the bottom face of the container? We know that the pressure is just the force all over the area concerned. In this example, we are to take the pressure at the bottom of the tank, so the area to be considered is width by length of the tank, or that is 2 by 3, giving us 6 square meters. The force will be computed as the fluid's weight, or that is mass multiplied by the gravitational pull. But how are we going to measure mass? Take note that the fluid is water, so we can solve for its relative mass with the formula of density, which is mass over unit volume, and that is 1,000 kilograms per cubic meter for water. So, by using mass of water as its density times the volume, we get 1,000 kilograms per cubic meter times 2 meters times 3 meters times 1.5 meters, which is equal to 9,000 kilograms. And now that we know the mass, we can multiply it with G and divide it with the area of the base of the tank, which is 6 square meters, giving us the answer of 14,715 pascals. Another thing to consider with fluid pressure is Pascal's principle, stating that any pressure applied to a confined fluid will be transmitted undiminished to all parts of the fluid. So, in a confined system, regardless of size and shape, the pressure will be the same all throughout every part. So pressure 1 is equal to pressure 2, or that is F over A of 1 is the same as F all over A of 2. The last parameter to be introduced is buoyancy, or the phenomenon which pushes an immersed object up with an upward force known as buoyant force. Buoyancy can be depicted on a massive ship which floats on water, whereby a needle sinks when dropped in water. To illustrate buoyant force, an object dropped in a denser fluid becomes lighter because of the buoyant force which acts on the object's weight. Buoyant force is the weight of the fluid displaced, which is then given with the formula density of the fluid times G and multiplied by the volume displaced. This is the principle discovered by Archimedes as he dipped in his bath. He discovered that the volume of fluid displaced is equal to the volume of the body immersed. Here is a buoyancy example. A 5 kilogram block of aluminum with density of 2,700 kilograms per cubic meter is attached to a rope. Determine the following. A. The tension force in the rope if the block is in a vacuum. B. The tension force if the block is in air with density of 1.29 kilograms per cubic meter. And C. The tension force if the block is in water with density of 1,000 kilograms per cubic meter. For the first requirement, the aluminum is placed in a vacuum, where there is no medium affecting it. So the tension force is plainly just its weight, or T is equal to W. Weight can be expanded as mass times G, or that is, T is equal to M times G, which gives us 5 kilograms times 9.8 meters per second squared, or T is equal to 49 newtons. When the aluminum block is placed in air, although minimal, there is a buoyant force acting to it in addition to its weight. So, by summation of vertical forces, we have tension plus buoyant force less weight is equal to 0, or tension is equal to weight less buoyant force. As we derived earlier, buoyant force can be computed as density of the medium times G times displaced volume. But what is displaced volume? The displaced volume is equal to the volume of the block, and we can solve it by using the density of the aluminum, which is equal to its mass all over its volume. So, 2,700 kilograms per cubic meter is equal to 5 kilograms all over volume of the aluminum, and the volume would turn out to be 0.00185 cubic meters, which is also the displaced volume. Now that we have the volume, we can solve for the buoyant force as buoyant force is equal to 1.29 kilograms per cubic meter times 9.81 times 0.00185, which would turn out to be 0.0234 newtons. So plugging in the buoyant force to the general equation, we get T is equal to 49 newtons less 0.0234 newtons, and T is equal to 48.9766 newtons. The last requirements approach is similar to the previous, which would use summation of forces equal to 0, and that is tension is equal to weight less the buoyant force. We had solved the volume of the aluminum block as 0.00185 cubic meters. So the buoyant force of water is taken as 1,000 times 9.81 times 0.00185, giving us the value of 18.1485 newtons. Then, in the general equation, we get T is equal to 49 newtons less 18.1485 newtons, so tension would be 30.8515 newtons. Check out Module 10, which is heat transfer.